Hello everyone. In this video, we will discuss about the concept of segmentation with paging, which means we have combined the both the mapping technique is said to be segmentation and paging. So we discussed about the paging and segmentation. So the comparison between the paging and segmentation or paging can be used for fixed partition, whereas segments are used in unequal size partition, which means it is not said to be all the partitions are equal in size. Based on the segments, whatever we are actually giving is said to be the based on the segment size the memory will be allotted. So it is unequal sized partition, and paging is said to be the static partitioning, whereas segments comes under dynamic partitioning. Only at the time of getting the process into the memory, we are just allotting the space for that process that is actually the given to CPU for execution. So only at that time we are allotting memory space for the incoming process. So these are all some of the differences between paging and the segmentation. So one more major difference between paging and segmentation is paging is a contiguous memory allocation, whereas segments are said to be non-contiguous memory allocation, which means randomly we can allot memory for the incoming segments. Okay, so based on the conceptual structure of the programming or the process, we can divide the process into several number of segments, and all those segments will be stored into the main memory. So here no overlay concept will be followed in case of segmentation, whereas in paging we can follow the overlay concept. So what is the overlay concept? Which means if any of the partition of the process is not in main memory, it is not available in main memory, so we have to swap the other partition of the same process, and the remaining partition whatever we need to execute, so only those partition will be brought into the memory from the secondary device. So this is what overlay concept. Only during the execution we are actually making this transformation from secondary device to the main memory, but this overlay concept is not there in segmentation, which means if you want to execute any one of the process and that process has been divided into several segments, only if it has enough space to hold all the number of segments completely at a time, so then only we can fit that process into the main memory. So no overlays will be followed in case of segmentation. So now we will see about, in some cases there will be a situation which is used to combine the both the concept of paging as well as the segmentation into one. So what are all the architecture which we need, which means some of the segments are not available in main memory, means we need to transfer it. And also if the and also why we are going with this concept segmentation with paging, so which means we are actually getting a fragmentation problem even in case of paging, but here in segmentation we just got the external fragmentation problem. So which means we will be dividing the memory according to the size of the segments, and if suppose if any of the segments which we have completed its execution, so we are not going to use that segments further in that was already resided in main memory, so which we are going to swap that old segment with any other new segment. So what happens there, the size of the old segment is larger than the new segment size. So if the new segment size is such a smaller segment, so if we are just allotting the same space whatever we have allotted previously to the old segment, so what happens here, lot of memory will be wasted because we have divided already, the partition has been divided already. So just we are swapping the new segment, but the new segment size is such a smaller size than the old segment. So we are just storing this new segment into the same allotted space. So in that case the lot of the remaining memory space will be wasted. So that is nothing but external fragmentation. So after storing some of the segments into the particular partition, but even then we have some more free space will be there in the same partition, but which does not fit into any new incoming segments because its size is smaller in smaller, so it is not possible to hold any of the segments. So in that case we are getting this external fragmentation. So once we are for if we follow the compaction technique, we can solve this external fragmentation. So we can avoid such a fragmentation problem. So if you go with the segmentation with paging, so we are having the fixed size of segments, and all those segments will be embedded with the paging concept. So each and every segment will be paged. So that is what segmentation with paging. So here the earlier architecture, which is nothing but the Motorola and the Intel 8086 and the Intel 386, all these things has been followed the memory model as a combination model, which is nothing but paging and segmentation. So in these kinds of architecture, which we have used the IBM OS by 232-bit version operating system. So in this, if you use how many number of segments we can have, which is nothing but 16k number of segments, and each segment size is larger than 4 gigabyte. And what could be the page size? So here we have the page size as 4 KB. So here the logical address space has been divided into two partitions. So if you look at this, the logical address space has been divided into two partitions. So in the first partition it consists of 8k number of segments, and in the second partition it consists of 8k number of segments, which means we have equally partitioned this logical address space. So what is the meaning of this LDT and the GDT? First of all, I will tell you why we are going with this descriptor table. Descriptor table is the table which indicates that a particular segment is available in main memory or not. So whatever the segments, because we are just combine the concept of paging, so we need to follow whatever the techniques we have followed under paging. So all those things will be followed in this concept. So again we'll be getting that overlay concept, otherwise some of the segments is not available in main memory currently. So we need to transfer that from secondary disk to the main memory. So if the a segment is not available or it is available in main memory, so that information will be represented by this descriptor table. So that's why we have this descriptor table here. And we have actually two categorization of descriptor table. The first one is local descriptor table, and the next one is global descriptor table. Local descriptor table, which is nothing but the if the process or the segments that were present in main memory, and it belongs to one particular process, that is nothing but local descriptor table. Suppose if the segment is available in memory and it can be shared by many other process, which means global descriptor table. So which we are just differentiating these two kinds of segments with the help of this local descriptor table and global descriptor table. So global means we are just sharing that particular segment by many other process, whereas local is nothing but it belongs to a single process. This is what the difference between these two descriptor table. So this is what the partition how we have done in case of logical address space. Now how we are representing the logical address, so it could be represented by two it could be represented by a pair of fields, which is nothing but selector and the other one is offset. Selector is nothing but it will have some selector information, and the G is nothing but which is nothing but the segment number. So whatever the segment you're going to select it for execution, so G is nothing but the descriptor information. So whether it belongs to the LDT, that is local descriptor table, or a GDT, that is global descriptor table, followed by this P is nothing but the protection. So this is the bit which is used to represent the protection of the segment. So what kind of access which we can perform in this particular segment is either it's a read access or write access or read and write or execute access. So in this way we are just mentioning what is its protection, and how many number of bits we are representing for selector is nothing but 13, and one bit is used to represent the descriptor table and which type of descriptor table it is. So that information we can get with this field, and the third field which holds two number of bits to represent the protection. And the next one in the offset, this is which is nothing but the selector, and which holds 16 bits in order to represent it. So 13 plus 1 plus 2, which is nothing but 16 bit. So an offset is the next field that we have to represent in case of logical address. So the number of bits which is used for representing offset is nothing but 32-bit number. So here, how many number of segment registers we can have, which is nothing but 6 segment register. So each and every register will be holding the base address of all the segments separately, which is nothing but segment register. Okay, so each and every register will be holding the base address of each and every segment. That is what 6 segment register. So each and every process consists of 6 segments. So here, in the segment table, we will be following these two kinds of register, which is nothing but limit register and base register. So base register, which is used to hold the starting address of that particular segment, whereas limit is used to hold the size of that segment, or it could be a length of the segment. So these two register, which is used to avoid the user to access any other segments, which is nothing but any unauthorized access can be avoided with the help of this limit and base register. This we discussed already in the segmentation itself. And here, what kind of paging structure we are going to follow in this method? So particularly in this in this architecture, so we are just following this two-level paging scheme. So two-level, which comes under the multi-level paging structure, isn't it? So it consists of actually two-level. So here, if you look at here, what could be the address format, or the representation which we are going to mention for the logical address. So here it is actually consists of three fields. The first field represents the outer level. So since we are using two level, so which means the first level, and it is the second level, or it could be a inner level. So the page number that we can get, that is a P1, and it holds 10 bits, and P2, it is nothing but the page table address, the corresponding frame number which we can get it from this page number, that is P2, and it is again holding 10 bits to represent these address, right? So these numbers, page numbers, followed by the offset field. Offset field we all know, which is nothing but the page offset. So the address of any particular byte which we want to fetch it from the corresponding frame. So that is what offset. So this offset value will be copied as it is with the frame number, and finally we'll be getting the physical address. So this is how the segmentation with paging concept will be followed in case of earlier architectures like Motorola and IBM OS, like that. Okay, so now we will see one example for the segmentation with paging. So it is given as Intel 80386 architecture. So in that architecture they have used this combination technique. So let us see how it works. So what could be the hardware segmentation with paging hardware, what is the working principle of it? Let us see. So here we have the logical address has been represented with these two fields. One is selector and another one is offset. And this selector has been represented with three separate fields, which is nothing but the segment number, that selector number, and followed by the G, which is used to represent the descriptor information, and followed by the protection. So all these represent information will be provided with the help of the selector, followed by the offset value that we can get in the second field. So using the selector value, so which we can understand which kind of descriptor table it is, either it is a local descriptor or global descriptor, so that we can get it easily. So we can access any of the segment descriptor. So this descriptor table, which provides you the information about whether the segment is available in main memory or not. So if it is available, we can get its segment number. Otherwise, we need to transfer it from the secondary disk, and that will be added with this offset value. So and afterwards we'll be getting the page number, because each and every segment has been paged. So again we need to represent what could be the page number. So here in this architecture, tool level paging structure has been used. So what is the address representation format for tool level paging structure is nothing but the first field which is used for representing the page directory, and the next one is page number and followed by the offset. So from the page directory we can get the particular directory entry, and from that we will be getting the page table entry. So the corresponding to the corresponding page table entry, so if you access it, we will be getting the corresponding frame number with that entry, and the frame number will be added with this offset value. So that is what we are doing here, and we will be getting the final physical address. So here we will be having the page directory base register. So for each and every table whatever we have, we should have its base address, which is nothing but the starting address, and that will be stored in any of the register. Then this register name is nothing but page directory base register. So even for the segment table or the segments whatever we have in main memory, we will be having separately the segment register in order to hold its starting address. So this is how this Intel 80386 architecture is following this segmentation with paging concept in order to do the mapping between the logical address and the physical address. Thank you.